Selamat pagi Bapak Ibu serta webinar yang sudah bergabung. Selamat datang di webinar series Clean Energy and Advanced Materials ke-16. Kami informasikan bahwa webinar akan segera dimulai. Kami mohon kesediaan Bapak Ibu untuk memastikan mikrofon dalam posisi mute selama acara berlangsung, serta menggunakan virtual background yang sudah kami bagikan di kolom chat. Terima kasih atas perhatian Bapak Ibu. Acara akan segera kita mulai dalam 1 menit lagi. Baiklah Bapak Ibu, acara kita mulai. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera bagi kita semua. Yang kami hormati, Bapak Dr. Hari Devianto, Deputi 1 Indonesia Fuel Cell and Hydrogen Energy atau IFHE, Bapak Profesor Dr. Jarod Raharjo, Ketua Kelompok Riset Material Fuel Cell dan Hidrogen Badan Riset Inovasi Nasional atau BRIN, sekaligus Sekretaris Jenderal IFHE, Bapak Dr. Rian Ahmad Budiman, peneliti dari Pusat Riset Material Energi BRIN. Yang kami hormati pula para narasumber kita yang luar biasa pada hari ini. Our warmest greeting to our speaker, Profesor Tatsuya Kawada from Tohoku University, Dr. Mahendra Rao Somalu from Linus, Malaysia. Welcome to our webinar series. Serta tidak lupa yang kami hormati dan banggakan, hadirin seluruh peserta webinar yang berbahagia. Pertama-tama, marilah kita panjatkan puji syukur kehadirat Allah Subhanahu wa Ta'ala, Tuhan yang Maha Esa, karena atas rahmat dan karunia-Nya kita dapat hadir dalam acara webinar ini dalam keadaan sehat walafiat. Kami ucapkan selamat datang di acara webinar e-Talks ke-16, webinar series on Clean Energy and Advanced Materials, yang diselenggarakan oleh Indonesia Fuel Cell and Hydrogen Energy dan Kelompok Riset Material Fuel Cell dan Hidrogen, Badan Riset dan Inovasi Nasional. Terima kasih kami ucapkan kepada Bapak Ibu seluruh peserta yang telah berkenan hadir pada acara webinar hari ini. Kami informasikan bahwa webinar kali ini disponsori oleh PT Yoki Electric Instrument, PT ITS Science Indonesia, dan PT PLN Nusadaya. Terima kasih kami ucapkan kepada seluruh sponsor. Acara webinar ini juga merupakan rangkaian Road to Global Hydrogen Ecosystem Summit yang akan diadakan bulan Juli tahun 2026 mendatang. Bapak, Ibu, dan hadirin yang kami hormati, sebelum acara dimulai, izinkan saya selaku pembawa acara untuk membacakan susunan acara pada hari ini yaitu sebagai berikut. Acara pertama, pembukaan, selanjutnya menyanyikan lagu Indonesia Raya, sambutan oleh Bapak Dr. Hari Devianto, kemudian foto bersama, dilanjutkan sesi utama webinar yaitu presentasi dan tanya jawab dipandu oleh Dr. Rian Ahmad Budiman. Setelah itu penyerahan sertifikat kepada moderator, pengumuman door prize, dan terakhir penutup. Baiklah Bapak Ibu dan hadirin sekalian, marilah kita mulai acara ini dengan membaca basmalah bagi yang beragama Islam. Bismillahirrahmanirrahim. Semoga acara pada hari ini dapat berjalan dengan lancar dan membawa manfaat bagi kita semua. Baik Bapak Ibu dan hadirin yang kami hormati, acara selanjutnya yaitu menyanyikan lagu Indonesia Raya. Hadirin dimohon untuk mengambil sikap sempurna dan marilah kita bersama-sama menyanyikan lagu Indonesia Raya. Baik, terima kasih. Bapak, Ibu, dan hadirin sekalian, acara berikutnya adalah sambutan yang akan disampaikan oleh Bapak Dr. Hari Devianto, selaku Deputi 1 Indonesia Fuel Cell and Hydrogen Energy. Kepada Bapak Hari Devianto, dengan hormat kami persilahkan.
Ya, terima kasih Mbak MC yang saya hormati Pak Jarod dan tim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone. It's a great pleasure to welcome all of you to eTalk 16 with the team Clean Energy and Advanced Materials. I'm delighted to see so many participants joining us from different institutions and countries, reflecting our shared enthusiasm for advancing clean and sustainable energy technologies. This event is proudly hosted by the Indonesian Fuel Cell and Hydrogen Energy, IFHE, and the Research Group of Materials for Fuel Cell and Hydrogen, BRIN, as part of the Road to Global Hydrogen Ecosystem Summit in 2026. Through this series, we aim to build connection, share knowledge, and strengthen collaboration among researchers, industries, and innovators in the hydrogen and clean energy fields. Today, we are honored to have two distinguished speakers, Professor Tatsuya Kawada from Tohoku University. Welcome, Prof, and also Dr. Mahendra Rao Somalu, from Linas, Malaysia, who will share their insights on solid oxide fuel cells, electrolyzers, and the vital role of rare earth materials in advancing these technologies. As we know, advanced materials and rare earth elements are key to improving efficiency and enabling the global transition towards sustainable energy system. We hope today's discussion will inspire new ideas and collaborations that contribute to this exciting global movement. I would also like to extend my sincere appreciation to our organizing committee for their dedication and to our sponsor, PT Hioki, PT ITS Science Indonesia, and also PLN for their generous support in making this event possible. Thank you once again to our speakers, moderators, and all participants for joining us today. Let's enjoy the session and continue working together towards a cleaner, greener future. With that, I am pleased to officially open the eTalk 16. Thank you very much.
Baik, demikian tadi telah kita simak bersama sambutan dari Bapak Dr. Hari Devianto selaku Deputi 1 Indonesia Fuel Cell and Hydrogen Energy. Kepada Bapak Hardev, kami ucapkan terima kasih atas sambutannya. Kita berikan tepuk tangan virtual untuk beliau. Oke, baik. Baik, Bapak Ibu dan hadirin sekalian, sebelum melanjutkan acara, mari kita abadikan momen kebersamaan kita pada hari ini melalui sesi foto bersama. Next is a photo session. So, kami mohon kesediaan seluruh peserta untuk mengaktifkan kamera terlebih dahulu. Bagi yang belum mengaktifkan, sekali lagi kami mohon untuk mengaktifkan kameranya agar wajah Bapak Ibu bisa ikut terekam di dokumentasi webinar hari ini. Dan kami mohon bantuan kepada panitia yang bertugas untuk mengambil foto. Baik, saya hitung dimulai dari 3. Halaman pertama, 3, 2, 1. Oke. Halaman berikutnya mungkin. Oke, tetap tersenyum ke arah kamera Bapak Ibu. 3, 2, 1. Oke. Oke, baik. Selanjutnya halaman terakhir. Tetap tersenyum ke arah kamera. 3, 2, 1. Oke, baik. Sudah seluruhnya diambil foto pada hari ini. Dan semoga hasil fotonya nanti bisa menjadi dokumentasi dari webinar kita hari ini. Baik, Bapak Ibu dan hadirin yang kami hormati, kita memasuki acara inti webinar kita hari ini yaitu presentasi dan diskusi. Sebelum itu, perlu kami sampaikan bahwa akan ada door prize untuk 3 orang penanya terbaik. Jadi, Bapak Ibu jangan lewatkan kesempatan untuk bertanya pada sesi diskusi nanti. Kami informasikan bagi Bapak Ibu yang terlempar keluar dari Zoom dan kesulitan untuk bergabung kembali, maka dapat bergabung dan menyimak melalui kanal YouTube IFHE Official. Acara ini juga kami siarkan secara langsung via YouTube IFHE dan dapat Bapak Ibu simak kembali setelahnya. Kami informasikan juga kepada Bapak Ibu dan hadirin peserta sekalian, untuk link presensi akan di-share di kolom chat saat tanya jawab di sesi yang kedua nanti. Dan kami mohon kesediaan Bapak Ibu untuk berkenan mengisi daftar hadir. Untuk daftar hadir hanya dapat diisi 1 kali saja. Kami mengingatkan Bapak Ibu untuk memastikan data-data yang telah diisikan telah sesuai karena akan digunakan untuk data pada sertifikat peserta. Dan sekali lagi kami mengingatkan kepada Bapak Ibu yang baru bergabung mungkin untuk menggunakan virtual background yang telah kami sediakan dan kami bagikan di kolom chat. Demikian kami sampaikan dan terima kasih. Baik Bapak Ibu dan hadirin sekalian, untuk sesi presentasi dan diskusi atau tanya jawab kali ini akan dipandu oleh Dr. Rian Ahmad Budiman. Beliau adalah peneliti dari Pusat Riset Material Energi di bidang Solid Oxide Cell. Baiklah, Bapak Ibu dan hadirin sekalian, selanjutnya izinkan saya menyerahkan acara kepada moderator, kepada Dr. Rian. Kami persilahkan untuk memandu acara.
Oke, terima kasih. Selamat siang semuanya. Perkenalkan, saya Rian Ahmad Budiman dari BRIN. Hari ini saya akan memandu 2 presenter. Kita mempunyai 2 pembicara dari Tokyo University dan juga dari Linus. Untuk presentasi pertama akan diberikan oleh Profesor Tulsia Kawada. Kalau bisa saya, can you hear me?
Yeah.
Okay, so good morning, Kak Sensei. So long time no see.
Hi.
So, we will start the presentation. So we have two presenters today from Tohoku University and also from Linus. So we will start from Professor Tatsuya Kawada, from Professor Kawada of Tohoku University. So before we start the presentation, I would like to remind everyone to turn off their microphone. Saya ingin sebelum kita mulai presentasi, saya ingin mengingatkan untuk mematikan mikrofonnya selama acara presentasi berlangsung. Selain itu, setelah presentasi akan diadakan question and answer, diskusi. Lanjutkan dengan diskusi, setelah itu akan dilanjutkan oleh presenter kedua, dan setelahnya akan dilanjutkan dengan diskusi dengan presenter kedua. So for today presentation, so after your presentation, we will follow by the question and answer or discussion. For maybe the audience have some question after that, so you can send a question by raise your hand, or you can give a comment on the chat box. Untuk memberikan pertanyaan, bisa untuk audiens bisa mengajukan angkat tangan atau memberikan komentar di chat box. Nanti akan kita bacakan. Oke, sebelum saya mulai, saya akan membacakan biografi dari Profesor Tatsuya Kawada. So before you start the presentation, I will read your biography. Professor Tatsuya Kawada is a professor of the Graduate School of Environmental Studies at Tohoku University, Japan. He received his PhD from the University of Tokyo and has been a faculty member at Tohoku University since 1995. His research focuses on high temperature electrochemical energy conversion device, such as solid oxide fuel cell, SOFC, and solid oxide electrolysis cells, SOECs, with particular emphasis on electrode reaction, ionic transport, and the mechanical durability of ceramic materials. Professor Kawada has authored numerous peer-reviewed publications and has supervised numerous graduate students and researchers who are now active in academia and industry. And he currently serves as the president of the Solid Oxide Fuel Cell Society of Japan and director of the SOEC Social Implementation Center, SOCIS, at Tohoku University. Through his pioneering work on functional oxide and high temperature energy system, he has made significant contribution to the advancement of sustainable energy conversion and storage technologies. So, Professor Kawada, you can start anytime for the presentation.
Okay. I'd like to share the slide. Can you see the slide?
Yes.
Okay. Okay. Thank you very much, Jan, and all the organizers and moderators for inviting me to this symposium and giving me a chance to introduce my favorite technologies of solid oxide fuel cell and electrolysis cells. So solid oxide fuel cell is a high temperature fuel cell that can use the hydrogen, not only hydrogen, but carbon monoxide or methane as a fuel and generate heat and power. And also the solid oxide electrolysis cell is the inverse reaction of a SOFC that uses the heat and power to generate hydrogen and carbon monoxide from hydrogen, H2O and CO2. So this talk have three parts. The first part is my introduction, very short introduction, and the next one is the short introduction of the solid oxide fuel cell and solid oxide electrolysis cell. And I'll talk about the structures and materials and how it operates. And then I'll introduce its history and current status. Probably it will be from the website reports. So not my original works, but and the third part is why do we choose SOFC and SOEC rather than the other types of fuel cell and electrolyzers? So I'll talk about the thermodynamics and kinetics and its advantage to other technologies. So who am I? I'm already Lian introduced me, make some introduction, very kind introduction. So not much things to add, but my country is here, Japan, and my university is located in Sendai City, here in a little bit north, about 300 kilometers north of Tokyo. And as Lian introduced, I'm now serving as the president of SOFC Society of Japan. You can see the webpage of SOFC Society, www.sofcjapan.org. So if many companies and academia people joins in this society from Japan and making the information exchange. So if you are interested in the situation of SOFC in Japan, please come contact me, and then I'll try to keep some connection with you. And another society is in the Tohoku University, that is SOEC Social Implementation Center. In that center, about 30 private companies are joining, and we also make the information exchange and some basic lectures from the university and introduction of the new technologies from the companies. You can also contact me to keep in touch with this society. So this is the introduction, and then I'll go to the what are SOFC and SOEC. So the materials of SOFC and SOEC are listed here. The main material, that is the electrolyte, is YSZ, that is abbreviation of yttria stabilized zirconia. So zirconia, the RO2, takes the monoclinic crystal structure in itself, but when it is doped with Y2O3 yttria, then cubic fluoride phase is stabilized. So this is the cubic fluoride, zirconia fluoride structure. And this material is the same as these things. This is a cubic zirconia that is not diamond, but the imitation of the diamond. It is a single crystal of yttria stabilized zirconia. And these knives and cutters are partially stabilized zirconia that has less amount of Y2O3, but it is very tough ceramics. So these all YSZ kind of YSZ, and our YSZ has 8 molar percent Y2O3 doped in zirconia. So in this material, 4+ ions of zirconium is replaced by 3+ yttrium ions partially. So, 4+ is replaced by 3+ means we are short and running short of the positive charge. So to compensate this change, oxide ion, that is a 2- ion, is moving out. So it has the oxygen vacancy. So one oxygen vacancy is formed per 2 yttrium 3+ ions. Then charge neutrality is kept. And interesting thing is the oxygen vacancy. That vacancy is or defect is our favorite thing. Perfect thing is not very important, interesting. And if you have oxygen vacancy, then oxide ion can hop into the vacancy, and then next another oxygen ion can hop into the left vacancies. So oxide ion can be transported through vacancy mechanism. That is the oxide ion conductor electrolyte. And for the fuel electrode side, we use nickel, but it is mixed with YSD particles. So it is used as the ceramics and metal composite. Nickel YSD ceramide is the typical fuel electrode material. And for the air electrode material, we use various types of perovskite oxide ceramics. So we use the porous ceramics here. The typical one is lanthanum strontium manganese oxide, or lanthanum strontium cobalt ferrite. These are, or lanthanum strontium cobaltite. These are the most typical air electrode materials. It depends on depending on the operation temperatures, the people choose one of those materials. And you can buy solid oxide fuel cell, single cell or stack from companies. Now, this isn't just an example, but the next series products can be purchased from the website, and also products from Ecogen, that is a company from Estonia, can be purchased from some other companies. In Japan, Magnex is selling their products. So now these are getting more and more popular, and you can probably purchase, sell, or its stacks. But still, it is expensive. And because the SOFC and SOEC are made of ceramic materials, they are basically fragile. So people try to make its cell and stacks in a safe way. So the various types of their stacks design have been invented. So it has planar type, or tubular type, or flattened tubular type. So these are explained in the history part. So this is the example of the operation of SOFC. Now it is for, let's say, this video is used for student recruiting or in the some university festival. So please just see. This is the solid oxide electrolyte. It is not zirconia, it is about ceria, but it is a similar one. And both sides we have the electrodes, and they are connected to this motor. And one side, upper side, is heated by this gun, and increasing temperature makes the oxide ion can move, and upper side is now using oxygen in the air. So upper side is the more reductive, and bottom side is more oxidative. So using that difference of oxygen partial pressures, this current is flowing. That is the principle of solid oxide fuel cell. So let's go to the history of SOFC, because the SOFC was first commercialized, or kind of commercialized, before SOEC. So the story begins from the invention of oxide ion conductor zirconia. But the zirconia, it was found that this is conductive at very high temperatures due to the oxygen vacancy mechanism. But it was used not for fuel cell first, but for lamps, because at the time, tungsten lamp was not very good due to the pure vacuum technologies. So high temperature heating, or high temperature resistive property of zirconia was very nice for making lamp. So Nernst, that is a famous electrochemist, Nernst invented a lamp here. And that patent was sold to Westinghouse company in US. And then Westinghouse people tried to make the fuel cells from this lamp. And first, hydrogen-fueled fuel cell was made by their technicians, and it was reported in 1962. And after that, in 1980s, Westinghouse successfully made tubular type solid oxide fuel cells. So their fuel cell is takes such kind of closed-end tube type, and they use substrate, porous substrate material, and on that substrate they make fuel electrode, electrolyte, and air electrode. And then the part of the fuel electrode, air electrode first, and electrolyte, and outside is fuel electrodes in this case. And the air electrode inside is connected to this interconnect material that is a lanthanum chromite based material, and it makes some line, longitudinal line, and that connects the cell of the next to the side by side. So it is connected in series in these directions and parallel in the other directions. And air is flown inside and fuel is flown outside, and it operates as the fuel cell. It was operated at above 900 degrees C. And this was the, in Japan, we call this is as the tatejima, and that means vertical or longitudinal line type material, fuel cell. And Mitsubishi Heavy Industry in Japan developed another type of tubular type cells. They also use the porous substrate, but on that substrate, they first makes the fuel electrode, and electrolyte, and air electrode. But they made the cell in some separated way. So it is a segmented in series type design. And both are tubular cells has the merit of easiness of the making gas sealing, because the tubular type has only sealing part only at the bottom or end of the tubes. In Mitsubishi type, both ends are gas sealed, and in the Westinghouse type, they have no tight gas sealing, but air is flown inside and go back from this between the inner and the outer tubes, and the exhaust air burns the fuel from this intermediate chamber and keep the heat or keep the temperature. So this is the tubular type, but the disadvantage of the tubular type was the long current pathway. So in this Westinghouse type, current must go through these peripheries of the tubes, and Mitsubishi type, it should go on the this side to the longitudinal directions through the cells. So it tends to have a high resistivity. So to reduce the resistivity, people try to make planar type cells. The planar type cell is more simple, and everyone would think about planar type for fuel cells, but it is ceramics, so planar type came after the tubular type in this case. And planar type is now used by the company, American company, Bloom Energy, and that is now selling very large amount of these SOFC products. And the first planar type was held by electrolyte plate itself. So it is electrolyte supported planar design. But in this design, the thickest part is electrolyte, and it has the high ohmic resistance. So to reduce the resistance, people want to reduce the thickness of the electrolyte, but it is fragile. So first, probably the people from the Jülich Center in Germany thought about the making very thin electrolyte on electrode material. In this case, anode for a fuel cell means the fuel electrode, that is nickel ceramic, and on that thin electrolyte layer is formed, and then air electrode is formed, and then the single cell is made. And this type of anode supported or fuel electrode supported planar design was used in several companies. For example, in Europe, Solidera, it is an Italian company, but it is originated from the Swiss spin-off companies, and it is combined with the Italian system companies, and now it is called Solidera, and they are using this type of the electrode supported cell. And also in Japan, Morimura SOFC company is using this type, and they are making very high performance cell. And the electrode supported cell has its merit in the thin electrolyte, but for making it very small applications, people want to heat up and shut down more frequently. In that case, normal planar type is not very good for temperature change. So Kyocera, a Japanese company, ceramics company, invented this flattened tubular type. It is a rather small tube, flattened tube, and it is connecting back to front like this. This is the cell stack, and this is a kind of flexible structure. Only one side is sealed, and fuel goes inside the tube, and it is burnt on the top. So this type of the cell is now used in the household SOFC combined heat and power system that is called NFARM Type S in Japan. And to make it more robust, Ceres Power, it is a UK company, invented the way of sintering cells on a metal support. So metal sheet is first prepared, and on that, anode, electrolyte, and cathode are sintered one by one. So this is not very fragile. It can be bent, and it can be heat up quickly and shut down quickly. So this is sold by Ceres Power, and that company is also making a good business. Now, trying to make a good business. And current status of SOFC development is the most successful SOFC maker are Bloom Energy and Kyocera or Aishin. So Bloom Energy has already sold a total 1.3 gigawatt of cumulative capacity of SOFC systems in US and in Korea. They have a collaboration with SK in Korea and making very good sales of the SOFC systems. And now they announced that they are making some facility to make 2 gigawatt SOFC systems per year. That is American company. And also another successful application was in Japan, NFARM Type S, as I already introduced. This is the picture of the household CHP systems made by NFARM. And the cell stack is fabricated by Kyocera, and it is a systemized system of that system. Stack is made by Aishin. So they already have sold 200,000 units. But one unit has a very small capacity, 700 watt. So the total production capacity was the best in Bloom Energy, but the total number of units was sold by Aishin and Kyocera. So this was the SOFC situation, and now many companies of SOFC makers are going to SOEC because they think that the SOEC can be expected to give larger commercializations, larger business. So one of the best companies is the Sunfire in Germany. So they are now built and started the demonstration of 2.6 megawatt systems in the Netherlands. And another big maker is Topsoe. This in Denmark. They already developed a very large facility to fabricate their cell stacks, and they are now trying to go into their business of the selling SOECs. The Sunfire's SOEC has the electrolyte supported type, and Topsoe's SOEC, they do not say clearly, but it is probably takes the fuel electrode supported type. And in Japan, national projects is running for methanation, methane making from the SOEC cogeneration. Cogeneration means the generation of electrolysis of CO2 and H2O together and make the methane as a alternative fuel. And also, the cogeneration can be combined with the Fischer-Tropsch processes to make the gasoline. So gasoline or oil makers in Japan are now gathering and to develop SOEC cogeneration and making e-fuel projects. And this is national project, and also the private companies are trying their own in development. MHI, Toshiba, Denso, Aishin, and recently Ebara entered the business together with Tohoku University. So this was the situation, history and present situation of the SOFC and SOEC development. But why do we choose SOFC and SOEC? Because it has a very high efficiency. This is the electricity generation or power generation efficiency of heat engines and gas turbine combined cycles as a function of power output size. So heat engine can generate very high efficiency, can make the high efficiency for generating power. But if the system size goes down, the efficiency goes down. But fuel cell can have the high efficiency at very low or very small systems. It is PEFC NFM, PE or PEMFC. But SOFC has even higher efficiency, 55% efficiency for 700 kilowatt system, 700 watt, 0.7 kilowatt system. And now Morimura SOFC company is now developing 65% efficiency system, very small system for hanging to the wall. So this will appear in 1-2 years, they say. And also other types of the systems have the around 60% of the efficiencies. So it is comparable to or higher than the highest efficiency of the heat engines and gas turbine, steam turbine combined systems. This is because the power generation mechanism is quite different from the heat engine. Heat engine uses the irreversible heat just to make combustion, and that heat is utilized to make the thermal cycles. But as fuel cell extract the driving force for the reaction, that is, gives the energy change directly from the fuel combustion reaction. So this is kind of a reversible system, making, balanced output of the driving force and the output power. So the mechanism is quite different. So in fuel cells, the total enthalpy can be extracted as power and heat. The maximum power extractable is that gives the energy change of the reaction, and that maximum heat extractable is the enthalpy change. But part of enthalpy is extracted as the gives the energy, and remaining part, that is entropy change part, is converted inevitably to heat. So it is, in this case, hydrogen and oxygen reaction makes three molecules, gaseous molecules, into two gaseous molecules. So entropy is negative. So negative entropy change of the reaction is a heat, and negative Gibbs energy change is the output power, and negative entropy change, this part, is inevitably going to heat. So what we can extract from the hydrogen combustion is Gibbs energy change here. Now I plot the Gibbs energy and enthalpy to the reverse way. I mean, the upper side is the negative values of Gibbs energy and enthalpy. So this part can be extracted as the power, and another part, remaining part of the enthalpy, goes inevitably to heat. So total enthalpy can be extracted as the power and heat. So if you see this chart, you will think that the lower temperature system will have the benefit, benefit, because the lower temperature gives higher Gibbs energy change. But actually, we have overpotential. Overpotential means the some loss of the potential due to the to promote the reactions. So high temperature systems has lower overpotential, so output power is a little bit higher than lower temperature systems. And this overpotential part, together with the reversible heat generation T delta S part, together will go to the heat. And high temperature systems has high quality heat generation. So this heat can be utilized very well. For example, if you use the methane as the fuel, it must be first reformed. And reforming reaction is endothermic reaction, so you need heat. This part of the heat you have to make some from somewhere. But if you use this product gas in a fuel cell, you will have heat. Then this heat can compensate the reforming heat. So only exhaust heat will be this size. And of course, you have some overpotential, so the heat of this part will be emitted. But the ideal efficiency of methane fuel can be counted as the 100%. So this was the power generation. But if you use it as the electrolyzer, the situation is also better, because in electrolysis, the power you need to decompose water to hydrogen is less than enthalpy change of water formation. That means if you have external heat source and you can use that heat, then power to enthalpy ratio, or enthalpy to power ratio, can go higher than 100%. So this cannot be achieved by the low temperature systems. But of course, high temperature heat source is not very common. And if you can't find out that kind of high temperature heat source, you can generate that heat by its overpotential. Yeah, you need anyway some overpotential. So if your overpotential is tuned to go to the enthalpy, then this system can be operated as the thermal neutral situation. So in that case, you don't need external heat, but heat generated by the overpotential can be used to maintain its temperature. In this case, also you need, of course, you need some external source for making steam from the water, liquid water. So this heat can be, but it is low temperature exhaust heat, so you can find some good source of this type of the heat. So this say thermoneutral operation of electrolysis runs how to say in a ideal way. It can run at 100% of efficiency. So actually, it runs at about more than 80% efficiency in a realistic systems. So the important part was the difference of the kinetic or dry over potential. This is a typical IV characteristics of the low temperature fuel cell. So it has very large over potential like at low current densities. But solid oxide fuel cell has not very over potential around the open circuit voltage. So almost linearly, the current can be extracted. So that is why we can have the very high efficiency fuel cell systems. So efficiency is higher for SOFC, especially with methane reform. And maximum power density can be somehow higher by PEMFC. But start but shutdown is easier for PEMFC, but precious metal will not be used in SOFC. So comparing those merit, for fuel cell vehicles, PEMFC is better, but for stationary generators, I believe that the SOFC is better. And for electrolyzers, it is the DOE target. So target values for kilowatt per kilogram hydrogen. So low temperature systems, the ultimate target is 45 kilowatt hour per kilogram hydrogen, but only solid oxide have 35 kilowatt hour per kilogram hydrogen. So it is much different. Of course, it is assumed that the water vapor was supplied. And the similar thing is also in the EU target. And also the SOFC can decompose CO2 easily, much easier than the low temperature systems. So it can be used as the cogeneration or of hydrogen and CO. So it is a co-electrolysis. And then if you can co-electrolyze CO2, you will be able to make methane or some e-fuels. So using these systems, maybe you can develop such carbon neutral or carbon recycled society in the future. Okay, that is all I have today. Thank you very much for your listening.
Thank you for your presentation. So we will move to discussion. If the audience has a question, so would you please raise your hand. Untuk yang sedang melihat presentasi, silakan jika ada yang ingin bertanya, boleh mengajukan angkat tangan terlebih dahulu kalau ada.
Pardon?
Any question? So if not, I will read some question from the chat box. So there is a question on Gunawan Unisula. So he asked, the fuel used in SOFC can vary as presented. If there are impurities in the fuel, will it cause a kind of crash on the anode? Does the SOFC system require high purity of 99.99% when using hydrogen fuel? That's the question. So if I summarize, the question is, what the effect of the impurities in the fuel? So is it really necessary to use 100%, almost 100% pure hydrogen in the fuel?
No. In a low temperature fuel cells, very pure hydrogen is necessary because the small amount of carbon monoxide will affect the catalytic property of platinum. But at high temperature system, CO can be used as the fuel itself. So CO is not the you do not have to clean up CO. But if you have sulfur containing gases, that is harmful for the fuel electrode. So you need to make use some chemical filter before the supplying the fuel to the the fuel cell. Maybe Lian is more familiar to that kind of impurity effect.
So, of course, the impurity will cause some effect on the anode, but in case of SOFC, we don't really need high purity. That's correct answer. Okay. So that's the answer. So I will move to second question from Erlangga University. So I will just summarize the question. So because SOFC compensation is, what to say, is quite expensive. And this depends on the material like yttria stabilized zirconia. So the question is, do you believe future advancement should prioritizing material substitution with more abundant element, even if it initially reduces efficiency to ensure long-term stability and ethical sourcing of solid oxide technologies? That's the question.
Okay, yeah. Our use of the rare earth is the very difficult part of the fuel cell. So maybe it can be solved by the next talk, maybe. But and the important part of the fuel cell is the electrolyte. And now some people are trying to make another more abundant material to make the electrolyte. But right now, zirconia is very, very stable and established technology. So it is very difficult to replace zirconia. But the thickness of the electrolyte can be not very thick. It can be made on some support. And if you use metal support cell, so you can use abundant stainless steel as a support layer, and you can use rather thin electrode layer and electrolyte layer. Then all the material cost will be less than the normal electrolyte support or electrode supported cells. So people now are trying to develop metal supported cells for reduced cost systems. That is one of the direction to go to the lower cost.
Thank you for the answer. I will move to next question, is it okay? So the next question from Galuh, Pelajaran University. So she asked about As SFC technology continues to scale up in industrial application, how are the issue of the end-of-life recycling and material sustainability being addressed, especially regarding ceramic and rare metal components? So the question is, because we scale up the SOFC in industrial application, so there will be an issue of the recycling of the material or component of SOFC. So how we address this issue in this field?
Yeah, actually, I'm not familiar to the recycling technologies, but the probably the materials used in SOFC can be recycled. Zirconia can be separated with the other materials, like because, for example, air electrode is made of lanthanum cobalt oxide or lanthanum iron oxide. It can be dissolved in the acid, and zirconia will stay. And anode side, you can etch the nickel part easily by the acid. So probably making recycle from the used cells will be not very difficult, I guess. But I'm not very sure because I'm not familiar with those technologies.
So, but also these technologies, I think, also developed for the batteries as well. I heard some researchers working on the recycling of the batteries part of, especially for lithium or nickel. So I think in the future, maybe we will see this kind of technologies. And there's someone who has hand. So Pak Utama Kajo, silakan jika ingin bertanya.
Pak Moderator, bahasa Indonesia aja ya. Saya kira saya kampungan. Jadi gini, saya bertanyanya kepada profesor, tidak secara detail teknis, tapi lebih umum. Pertama, di Jepang, di dalam proses pembuatan komponen-komponen tersebut, apakah bahan dasarnya itu ada di Jepang atau mereka impor? Yang kedua, pertanyaannya, berapa ukuran yang paling mencapai keekonomian bagi satu stasiun, satu sentral pembangkit, dan ukuran berapa yang paling cocok untuk kebutuhan rumah tangga, untuk ukuran keluarga sedang gitu. Itu aja Pak, 3 Pak. Terima kasih Pak.
So I will translate the question. The first question is, in Japan, when the industry fabricate or make the SOFC system, especially on the SOFC component materials, so where did Japan get this component? Is it the raw material come from Japan itself or from another country? So I think that's the first question.
Okay. Japan will buy most of the raw materials from other countries. Yeah, some Japanese companies have some mines in the other countries. So they will develop, for example, nickel from some part. But the mostly raw material itself is not from Japan. So we'll buy. Is it the answer?
Yes,
Iya Pak, sudah terjawab Pak. Jadi kalau nanti dia butuh nikel, nanti saya kirimkan buat dia. Berapa banyak maunya? Banyak di Indonesia. Ya, makasih Pak. Lanjut Pak, nomor 2 Pak.
So the second question is that in the case of SOFC power output, I think he asked about the power output, the power which is the best power output that can be used in a residential house. So I think the question is a bit it's from the economical side instead of the technological side. So that's do you catch the question? So what is the best system size? Is the best size in the term of the power for the SOFC for the residential house? I think it depends for each country.
Yeah, depends on each country, and also depend on the size of the house. If you use much amount of hot water, then yeah, SOFC system can generate, it can be used as a cogeneration system, and you may be able to reduce the use of energies. So if energy price is getting higher than the present situation, then you will have merit of having SOFC systems. But right now, actually, the capital cost is too high for SOFC systems, so it's very difficult to get back the initial cost from the merit of the reducing the energies. So many systems now sold in Japan was built when the new house was built. So if the price is together with the other parts in the building house, then people will not so much care about the price. But that is a very important problem. So we have to lower the cost. Otherwise, it is very difficult to get more, introduce, I would say, penetration of this technology to the market.
Thank you. So, Pak Tamakajo,
Makasih,
jawabannya
Pak.
tergantung
Makasih, Pak.
dari tiap negara itu. Jawabannya. Okay,
Makasih,
thank you
Pak.
very much for the answer. Thank you very much for your answer.
Sampaikan aja pesan, Pak. Lebih baik dia ambil nikel dari kita langsung, Pak. Kita banyak daripada dia beli sama pedagang dari China. Lebih murah dari kita, Pak. Nikel, Pak. Terima kasih, Pak.
Yes. So Mr. Tamakajo said to you that if you want to buy nickel, so you can buy from Indonesia. It's cheaper than China. So I think we have one more question. If we still have time. So the last question probably. So we have to move to another presenter. So the last question is from State Electricity Company. So PLN. The first question is, what are the typical target application in Japan for SOFC system? That's the first question. Could you please answer this question?
Yeah, for SOFC system, the household, very small system was our first target. And people are trying to make the a little bit larger system used in office or some small industries, but they are not successful yet because the cost merit is more important for those kind of applications. So we have not yet successful in using the SOFC for those applications. So the people are trying to find some other things like SOEC. So in the case of SOEC, the companies people believe that they have more chance to get penetration to the business.
So the answer is that in Japan is residential housing for the application right now. But if we go to SOEC, it's possible to more large scale up.
Large scale.
So the second question is, how does the thermal management, stack design, and system integration differ from high temperature SOEC system compared to low temperature technologies? So the question is the thermal management, establishment and system integration difference between SOFC and high temperature fuel cell with the low temperature fuel cells?
Yeah, for fuel cells using the methane reforming fuels, the exhaust heat from the solid oxide fuel cell can be directly go to the heat required for water reforming reactions. So the hot box of SOFC is integrated with the catalyst of the water methane reformer. So it is probably the largest difference between the high temperature system and low temperature systems. Is it all right?
Yeah. That's all right. So that's the difference of the technologies in some of thermal management, stabilization, and integration. The third question is, what are the main challenges, technical, economic, material durability, integration for commercialization of SOFC and SOEC in Japan? The main challenge in commercialization of SOFC and SOEC in Japan, is it economic, material durability, integration, or something else?
The final challenges will be economic things. And before that, we are trying to tackle the challenges for the durability. During the national project, we are trying to make the more durable materials and more durable operation of the SOFC, SOECs. So the first target is the durability, and the final or next very important target will be cost reduction, I think. Is all right?
So cost and also durability is still one of the main challenge in SOFC. And the last question is, how the Japan energy policy targets drive interest in SOFC technologies? So is the question, what I understand is it what kind of Japan energy policy that can, how to say, support this SOFC technology?
Yeah, for SOFCs, government will support some part of the cost of installing your household system. They have some subsidies. And also, that is for SOFC now. And now they are going to shift to SOEC technologies, and now government will make some national project of helping development of the SOECs. So some, NEDO? NEDO is the kind of the development of those technologies. NEDO project is now supporting SOEC development, and also some sort of large fund will be supplied to the SOEC for company development, probably from next year or something. So government will focus on the SOEC support now.
The answer. So I hope that is enough for the answer. So I think unfortunately, we have to move to next presenter, although we have so many questions. Before we move to the second presenter, we would like to give you the appreciation. So please wait.
Thank you.
Please wait.
Thank you very much.
So this is the certificate of appreciation for you as a speaker. So we will take a picture. Yeah. So we will take picture of you with the certificate. Please wait. So let's finish. So thank you very much, Kak Sensei. So if you have another schedule, so feel free to leave the seminar. So we will move to second presenter now. Thank you.
Thank you very much.
So we will move to second presenter, Dr. Mahendra Rao Somalu. I think he already joined with us. So good morning.
Good morning, Budiman.
Good morning.
Yeah. Thank you, Bapak Budiman.
So I would like to read your biography. So before we start the presentation, I would like to read your biography. Dr. Mahendra Rao Somalu is currently a principal material scientist at Lynas Rare Earth Limited, located in Kuantan, Malaysia. He leads the research and innovation laboratory for the development of new products of various applications, including fuel cell and catalyst for ammonia cracking and high temperature gasification. Previously, he served as an associate professor at the Fuel Cell Institute, University Kebangsaan from 2012 to February 2024, before moving to industry. He was awarded the PhD degree from the Imperial College London in 2012, and he is an active associate member of the Institute of Chemical Engineer since 2013, a member of the Malaysian Associate of Hydrogen Energy since 2017, and member of the Malaysian Association of Solid State Science since 2019. He also received the Article of the Year 2021 award from the Hindawi for journal entitled Structure and Electrochemical Properties of Lanthanum Silicate Apatite, Lanthanum Silicate Apatite for Solid Oxide Fuel Cell, SOFCs, published in the International Journal of Chemical Engineering. He has received several awards, including the Best Researcher Award in 6th edition of International Research Awards in New Science Invention. He was awarded the Gold Award in the 4th International Malaysia-Indonesia Thailand Symposium on Innovation and Creativity 2021, and UKM Honorable Award 2019 in the Science category, a Silver Award in the 3rd International Innovation, Design and Articulation, etc. He has extensive expertise with over 19 years of experience in the development of high-temperature fuel cell technology, nanomaterial, biomass gasification, and hydrogen energy. He has published more than 150 scientific articles in various high-impact journals and has been invited as a keynote or invited speaker in various national and international conferences. That's the biography. Dr. Mahendra, are you ready to give a talk?
So may I start my presentation?
Yes, okay. Please.
I will share my slide.
Yes.
Thank you very much. Can you see my screen?
Yes. Please start the presentation.
First of all, I would like to thank the webinar series committee for inviting Lynas as one of the presenter for today's fruitful discussion. Also, I would like to thank IFAG for organizing such a beautiful seminars for the benefits of the community of fuel cell materials and many more. And on behalf of Lynas, so I would discuss today the strategies of Lynas in solid oxides for fuel cell electrolyzers technologies, especially for SOEC and SOFC technologies. So before I carry on this presentation, so I would like to see the overview of my presentation today. I think the introduction of fuel cell, Prof. Kawada already discussed clearly. We will move. We will skip some of the slides if it is very similar to Prof. Kawada. So in this presentation, I want to highlight the solid oxide cell operating condition, material selection, components and challenges, and then we will see the fuel cell electrolyzer projections based on the few consulting companies, their projection. And then hydrogen demand, cost, and technologies. So we will see some of the highlights in this area. And then electrolyzers demands. Then we will move for the cost estimation for the solid oxide stack production cost. From here, we understand where is the materials cost. And then we will discuss about the strategies of Lynas in business commercialization. And then I will discuss some overview of Lynas, about our capability and our alliance with Japanese company. And recently with the new MOU with Novion, US-based company on the magnet manufacturing. There's the new MOU that we made, I think 2-3 days ago. And then the current program at the Lynas on this specific program for SOEC, SOFC, and then we will see the synergism between the Lynas academia and industry. Okay. So I summarize all this in this for solid oxide materials based on the operating condition. This is a common view how the materials selection and then the cell configuration for three typical configuration with a metal supported cell, fuel electrode supported cell, and electrolyte supported cell. Okay, and the application is based on the operating condition as elaborated by Prof. Kawada, and then the material selection also based on the operating conditions. Okay, so if you see the low temperature, the traditional material is Syria-based material. For high temperature intermediate, so people normally refer to the zirconia-based material. Okay. And the Scandia stabilized zirconia-based material is very, very promising material for the intermediate operation. Okay. So it can deliver 3 to 4 times same power at the high operating temperature using this Yttria stabilized zirconia. That's the reason why the Scandia is very promising recently. Okay. So I just highlight a bit about the requirements. As we know, the electrolyte, the key requirement is the conductivity for the efficient ion conduction. For the traditional oxygen ion conducting, of course, we need high ionic conductivity. At any operating temperature, we need to make sure the ionic conductivity is sufficient for the operation of the fuel cell. And then the flow electrode, as we know, the electrode must have a good balance between the electronic ionic conduction. So this is very important. So mainly the electronic conductivity is very critical for the electron movement and then the ion movement, because the TPB areas is very critical for the electrodes on both anode and electrode side. So that's why the mixed ionic and electronic conduction behavior is very critical, and the tolerance towards sulfur poisoning, chromium, and then carbon deposition are also very critical to be considered when we use the materials and also for the operating of the fuel cell at any specific operating temperature. So eventually the both electrolyte and electrodes is very critical. They must be stable and chemically compatible with other components. This is very important for the durability. Okay, so the durability is very dependent and very, very important for long-term operation, as highlighted by Prof. Kawada now. I just highlight some of the problems, typical problems. There are many problems. These are very common problems that normally we face for the fuel electrode. Fuel electrode, the main problems we normally face are carbon deposition. So this is due to the carbon-based material that we use at the electrode. For example, for co-electrolysis, we use CO2. water and hydrocarbon fuel for SOFC. Of course, we will face the carbon deposition. And some of the potential solutions that many researchers that presented many papers, some of them is, they said, the new method that people currently is considering is the solution. Okay? Use metal exhaust perovskite-based materials to mitigate this issue. Okay, so this one we can use using the perovskite-based material with solution. And then there is other solution that already known where we use bimetallic electrodes by partially replacing the nickel with copper, cobalt, or something, this metal to reduce the carbon deposition. And in terms of operation, use high steam to carbon ratio also potential solution to mitigate the carbon deposition. And then in some of the works, they also modify the nickel surface by of a stable oxide layers such as ceria to reduce the carbon deposition. Sulfur poisoning, this is typically due to the presence of hydrogen sulfide in the hydrocarbon fuel. So this is a very important issue that we need to consider, as nickel can be easily poisoned by this sulfur to form nickel sulfide, and then it will deactivate the catalyst for the efficient oxidation of fuel. So again, people prefer to use some of the solutions such as alloying, ceria-based composites, okay, applying the coating as a noble material, such as noble metals. All these challenges, we need to have some solutions. So this is some of the solutions that proposed by many studies recently. So we know solid oxide fuel cell electrolyzer normally operates at high temperature. So we have some nickel coating effect. This is very common for the nickel-based electrode. Again, some of solution people looking at the perovskite-based material. Okay, so however, the challenge is again here is the high electronic conductivity for this type of the materials, and then they should try to use the nanostructured materials, and then applying the protective layer such as UDC and reduce the operating temperature. So these are some of the potential solutions for the fuel electrode. And then we know the redox instability is another issue, especially for the anode supported cell. So we know the microstructure damage due to the volume expansion when nickel is oxidized to nickel oxide. So again, people are looking at using the perovskite as a possible solution to mitigate this issue, and then thin film coating, for example, to avoid the oxidation of the nickel. So these are common challenges and opportunities that we need to consider when we're designing the materials or proposing some materials for the potential application, because these are common interests of most of the industries. And then in terms of electrolytes, as we know, the key for electrolytes is the first parameter is the conductivity. So oxygen ion conduction normally decreases significantly when you operate at a low temperature, especially for the zirconia-based material. So they propose the alternative material, scandia-based tablet, zirconia-based material, but the challenges is the scandia. So where to get? Scandia is expensive. So geopolitical issue here to get the scandia. So this is the key consideration that we need to consider before we propose this type of material. I think Bloom Energy, I think they use this type of material for their stack construction. And then the challenges is scandia, because scandia mainly coming from China. China currently do some restriction on the exporting of rare earths. Okay, so suppliers can play a critical role in this material selection. Okay. So dot area of for low temperature is very useful. And then we know lanthanum gallat is very good material, but they have some chemical stability issue due to phase separation. And then some of the opportunity is to reduce the thickness, to reduce the polarization resistance of the existing material. Okay, so this is some of the way of improving the conduction of electrolyte. And then we know there is some diffusion of lanthanum and strontium from the electron, resulting from the formation of the secondary phases such as lanthanum zirconium, strontium zirconium, manganese, lanthanum zirconia. So these are diffusion issues that we face when we use with air electrode. So some of solution we are very readily available, such as the barrier layers, okay, to reduce these interactions for the YZ materials. And lanthanum LSGM, you know, it is a well-known materials. However, you know, the chemical stability issue when it can form nickel lanthanum gallat phase when you operate at high temperature. This is we call the interface interactions. Okay, so this will decompose. It will change the composition ratio of this electrolyte material, and eventually it will reduce the conductivity of the LSGM. So this is why this material very good in terms of conductivity, but again, as I said, the stability and then the durability of material very important for long-term operation. So for Syria-based material, of course, we have some issue, especially the partial reduction of C4 to C3 positive when you operate at lower temperature, and then the partial oxygen issue. So this is another issue that we need to consider for Syria-based material, especially for series power. So they are using Syria-based material that is for the low temperature operation. So they have their own technology to mitigate all these issues. For oxygen electrode, so we know oxygen electrode, so we prefer to use perovskite-based material as the main selection, as highlighted by Prof. Kawada. So we know there is some of the issues such as the delamination due to the stress generation between the electrode and electrolyte. This is actually high oxygen partial pressure build up at the electrode interface when it is in the electrolyzer mode. So this less ability of electrode to conduct oxide ions and greater ability of the electrode to release the oxygen. So the stress generated between the electrolyte can delaminate the cathode from the electrolyte. And then pore formation. So we know during the SOEC operation, oxygen partial pressure at the fuel electrode is further lowered by the electrolysis current, whereas it increases at the air electrode side. Therefore, the high electromotive potential results in the formation of oxygen within the electrolyte grain boundaries. So this will cause the formation of in the electrolysis core. So we know the potential solution, people always propose the new materials findings. Okay, this is the common suggestion for many researchers. So yes, so we need to accept, but at the same time we can consider the other solutions in terms of the operations conditions. Also, we can mitigate this issue. And then again, crystal structure get distorted as the lanthanum and strontium metal diffuse into YZ network. So this is the structure changes. So due to the interdiffusion issue, as I highlighted before, this is another solution. That's the reason why they use the barrier layer such as GDC between the air electrode and electrolyte to mitigate this interdiffusion issue. So these are common challenges that we found out in most of the components in solid oxide fuel cell for the three principal components. So the current trend. So of course, the industry will look at the lowering the cost. Okay, lowering the cost, you mean lower operating temperature, so we can use less expensive materials, simpler manufacturing for cost sintering, and simpler systems. So this is the three main targets. So also some other methods available to lower the cost in terms of the material selection and increase the performance. Of course, we have a product we need to show the performance to our customer who are readily buy the technology for the power generation or for hydrogen generation. Okay, so again, the performance must be shown by the high conductivity of the electrolyte, and we can use more active electrodes, MIC electrodes, to overcome the oxidation reduction issue and then the carbon deposition issue. So many more issues at the electrode. And then exolution is one of the approach to mitigate most of the problems. And then the nanostructured materials, this is another solution. So there are many solutions we can consider to increase the performance. The durability. So again, we know the durability must be 1%, less than 1% or 1,000 hours operation. I think currently the DOE, I think the target by 2026 is, I think 0.5%, something like that. So again, the degradation is very, very critical to make sure the operation is between 40 to 50,000 hours, at least the operation of the stack. So how to improve this durability? So of course, operation temperature is the key. So, and then some of the poisoning issues such as chromium, and then the delamination issue among the electrolytes, and then interdiffusion issues. So all these is related to the chemical stability mainly. Okay, so we need to overcome the chemical stability to improve the durability of the cells. And then more robust materials. Okay, so for faster startup, so high temperature, we know we need a longer startup time, and then this is one of the challenges for the high temperature fuel cells or electrolyzers. And then the fuel flexibility for the solid oxide mode, fuel cell mode, is one of the what we call the advantages of the for the high temperature operation of solid oxide fuel cell. And then metal supported, we can operate at lower temperature. This is a series technology for the metal supported cell. And then oxidation, carbon and sulfur tolerant electrodes are very important. The material must show tolerance towards all these issues. And then we need to consider about the MIC electrodes, mixed ionic electronic conductors for the both air and fuel electrodes. And then we can minimize the steam requirement by direct hydrocarbon operation. So these are all these depending on the how robust the materials for this condition, under this condition. So this is the four trend that we need to look when we designing the materials or operating the stack for the high performance and long-term operation. So I move to the projections of the fuel cell market. This is from the IMARC consulting company that projected the fuel cell market. If you see this fuel cell market, the compound annual growth rate between 25 to 2033 is about 20%. Okay, 20%. From 6.3 billion USD in 2024 up to 44 billion USD by 2033. So this shows that the demand for for the alternative energy sector such as fuel cell very promising, okay, from this projection. And we can see about 25% of the fuel cell market is dominated by SOFC by 2030, which is a huge market for SOFC. If we manage to have a good supply chain of materials, this market will be boom very soon. Okay, I can say by 2026, solid oxide market is booming. Okay, you can see the Bloom going to do 2 gigawatt annual production. So that is the forecast that you can take as an indicator. All these big companies that moving forward. The reason this forecast is high because of the AI, because all the data centers need a lot of electricity. Okay, so they need a centralized power to support the electricity 24 hours. So the grid line power is not sufficient to support those. So the data centers, the AI technology attracted this technology in considerably people considering fuel cell to power the AI data centers. Electrolyzer market, similarly, so people are talking of decarbonization of industries, hydrogen fuel. So they need hydrogen for various ammonia production, green ammonia. So hydrogen is the key for the future green fuel environment with lower greenhouse gases. So if you see this, the global market is very high, about 95% projected by this Grand View Research Consulting Company from almost $500 million USD to 53 billion USD by 2020, which is a huge market. And again, you can see solid oxide electrolyzer is about 30% the dominant, the projection. Okay, the reason is most of the industries they need such as the steel industries, all this decarbonization takes place. So they need hydrogen and fuel cell, solid oxide fuel cell. We know very efficient in terms of the heat integration and then at the same time producing hydrogen or electricity. So in the big quantity. So that's why the demand for this market always a portion, I can say 25 to 20% for both fuel cell and electrolyzer market can be dominated by solid oxide cells. In terms of hydrogen production cost, based on the CO2 emission tax, if you look here, gray, blue, and green hydrogen. Green hydrogen production will require efficient, reliable, scalable, low-cost technology. So if you look for current scenario, CO2 emission per kg of hydrogen, of course, the gray will emitting a lot of CO2. Okay, if you look here, this top, and then the lowest is green hydrogen. But again, the cost of production is the key. Of course, in the current scenario, gray hydrogen is the cheapest, gray and blue, and compared to green. But by 2030, so green hydrogen production by water electrolysis will be very competitive in terms of cost with gray and blue hydrogen. If you see by 2030, the cost is very competitive. And then this is a trade-off with the CO2 tax. Okay, that's why the tax for the CO2 may encourage many companies shift to the green hydrogen production. Okay, by 2030 and by 2050, of course, the green hydrogen will be dominant in the market with a very competitive production cost. So this is we know about the technologies, why solid oxide electrolyzers is better than PEM and alkaline, already explained by Prof. Kawada. Okay, this is because of you know, the energy consumed by SOEC for hydrogen production is the lowest, which is about 30% less efficient, less electricity compared to other for low temperature fuel cell, where the heat generated will be used as a trade-off to the electricity in the SOEC mode. So that's the reason why the efficiency can go up to 95% compared to the low temperature fuel cells such as electrolyzers such as PEM and alkaline electrolyzer, which can go up to 60% only compared to 95% for SOEC mode. So this intrinsic thermodynamic advantage encourage the industries to consider this as a major technology for hydrogen production and co-electrolysis as well. I go for these electrolyzers demands based on the net zero emission. This is from the IEA 2023. If you look this technology, we know PEM and alkaline electrolyzer already in the market update. It's already mentioned, I can say, in the market update. And SOEC technology readiness is at the level 8, which is already in the going to enter the market for the market update. As I said, starting from next year, solid oxide will be booming in the market due to the competitiveness of this technology for large volume production, in addition to the heat demand in the industries. So if you look here, the unknown megawatt production by 2030. So the unknown is predominantly SOEC. So it's catching up very quickly with PEM and alkaline and overtaking beyond the 2030, the demand. So this is why this technology is very critical in terms of supply chain of materials. This is very critical, and Lynas can play a critical role outside of China for the supply chain. So these materials demand is very critical to ensure this technology is met in the market. In terms of the solid oxide, the material requirement, this is the projection by the IEA. If you see by 2030, they need about 50 kilotons of solid oxides, and it's projected up to 300 kilotons of solid oxide for the solid oxide electrolyzers, for example. So the demand is very high. As I said, starting from 26, if the market players try to establish this business in the market, as I show in this previous slide, is the market update scenario now. Okay, solid oxide will go to the market. Okay, from the demonstration to the market. So we know, as I said, 30% of green hydrogen comes from SOEC. Of course, 30%. The projection is consistent with some of the industries. You see, this is the some of the demonstration, I would say. 3.6 megawatt by Sunfire Bloom Energy also. So all these actually they are entering the market. Okay, this is mainly because of the decarbonization of the industries. So the tax exemptions, so many people think SOEC can play a critical role here. And then the solid oxide requirement per megawatt, if you see, this is just estimated. It depends on cell configuration at the same time. So we estimate about 300 kilogram oxides per megawatt. So this is a huge amount. If you compare with the 1.2 gigawatt power by the Bloom Energy itself. So the supply chain is very, very important for this type of material. including the recycling of the end of the life steps. So this is very critical role to ensure the sustainability of this technology in the market. I go for the cost. I want to compare how the cost of the material compared to the rest of the cost. If you look, the cost is very dependent of the manufacturing rate. Okay, if the manufacturing rate is very high, so I would say at least 1,000 megawatt. The production cost based on the 1,000 megawatt, I would say the material cost account for 50% for the both electrolyte support and hydrogen support. So based on this resource. So again, what I can say, the material is the key to the success of this technology in the industries. 50%, you imagine the cost compared to the rest. So Lynas can establish the supply chain outside of the Chinese source. Okay, so this is why the supply chain of materials is very important for the success of this technology, because the rare earth material is very, very important for this technology. Roadmap commercialization of solid oxide. First consideration is, of course, as I said, the materials. Refining the expertise and capacity is very important. And then the solid oxide production, of course, Lynas in this production. Recycling, hand of the stack, all the industries, they need this recycling technology to make sure the circularity of materials. Okay, so the recycling is very, very important. And Lynas, we have the know-how of this technology, how to do recycling of the end of the materials. We have our expertise and know-how of how to do this recycling, and this is very, very interesting for industries if you have the recycling itself. What are challenges for this commercialization of solid oxide? Resourcing, we call sourcing. How to source? Now the main supplier of most of the oxide is China. If China stops supplying materials, all these solid oxide business will suffer from the material. So that's why the second source is very, very important for most of the industries. So Lynas can play a critical role in the sourcing of the materials for these industries. Diversity, expertise, scalability, how to scale up. Of course, you need the materials and capacity. So this is very important. Opportunity. What opportunity we can create by this commercialization of the solid oxide? So we can create smart solid oxide supply chain, resilient and sustainable. So this is very important. So we are talking about performance, about the fabrication. This eventually, once we go to the industries for the gigawatts power, megawatts power, so we need to make sure the supply chain is established. Currently, the supply chain is playing very critical role for solid oxide commercialization. So partners data exchange is very, very critical. So this is very important. So to make sure this roadmap is materialized. And then the collaboration in innovation is very important. Forecasting, how the forecast for next 10 years, for example, we need to know that. And then procurement and then inventory planning is very important. And then end-to-end supply chain visibility. It needs to be very clear for the visibility of supply chain. Otherwise, this technology will be there forever. And then the transparency is very critical. This for the reliability, and then the self-mutual understanding about the partners is very, very critical. Where Lynas want to participate in this technology? So we know making cell, stack, module, and system. This is what happened in most of the in the common solid oxide technology. So Lynas is not interested and will not be competitors for the solid oxide industries. We want to be partners with the solid oxide manufacturers in terms of the supply chain. Okay, we want to supply the materials for the solid oxide electrolyzers of fuel cells, as we have that capability of producing the raw materials as a Lynas itself. So our role is very simple. We want to involve currently in this area, unit cell area. So of course, when you produce the material for your customer, you need to validate the materials. How to validate? So currently our role is production of solid oxide. And then of course, we want to test the material before we delivering the materials for testing with our partners. And then we want to positioning Lynas as an integrated company in terms of solid oxide production, testing and supply to the market. So this is the Lynas position in the solid oxide commercialization. We don't want to be a competitor for the solid oxide fuel cell. We want to be involved in the supply chain of the materials. Now I go some overview of the Lynas Rare Earths Limited. So if you see this map, so we have primarily the only new integrated source of Lynas Rare Earths from mine to customers, meaning we take from the mining and then we produce the raw materials from the end to end. So we have the capability of doing that. Okay, the only company outside of China, which is Lynas. Okay, so we own and operate Mount Well, the highest grade rare earths deposit in the world, which is located 35 kilometers south of Laverton in Western Australia. And then we have concentration plant, which is commissioned in 2011 and located 1.5 kilometer from the site. And then Lynas Advanced Materials Plant facility at the Gebeng, Kuantan in Malaysia. So this is actually we call Mount Well, and Mount Well is more on the upstream and LAM is the downstream to produce all the oxide, refining the materials, separation of the materials to all these rare earths oxides. So the capacity total production is about 22,000 tons per annum. And then we have currently first rare earths, heavy rare earths, TB and DY oxide from the Lynas, which is the only company producing outside China, the heavy rare earths, TB and DY for the magnet application, for example. So this is a huge achievement by the Lynas to sustain in this industry. So as I said, we are a only scale producer of separated rare earths outside of China. So we have the location in Australia and Malaysia, and we also have contracts signed with US for the rare earth separation. And I think a few days ago we have MOU with the one of the Texas-based company, the magnet manufacturing company, I think Novion, for the rare earth supply for the magnet industries. Okay, because all of these companies are suffering because of the current political issues. So Lynas fill the gap currently for all these demands. So this is what happened at Mount Well. So from mining until we get the concentrate. So this is the concentrate. This is the lanthanum. All the rare earths, mix of rare earths. So these rare earths from the processing, this is the upstream process from mining, crushing, screening, and then blending, grinding, flotation, thickening, filtration, and then bagging and transport to Malaysia for the downstream operation. Okay, from the concentration, then we have cracking, leaching, solvent extraction, and then precipitation, calcination, bagging, and storage ready for sale. So this is our traditional business in the current operation where we produce rare earths. So this is a summary of the flow as I showed before. So this is the range of the materials that Lynas produce. So lanthanum, cerium carbonate, lanthanum, cerium oxide, cerium carbonate, lanthanum oxide, samarium, samarium, europium gadolinium oxide, the mixer, NdPr, cerium chloride, lanthanum, cerium carbide, and currently we have heavy rare earths, TbDy, Tb and Dy oxides. So that is the starting from this April. So we already produce heavy rare earths, and we already have commercialization for those two heavy rare earths. So that is some value added to the Lynas business. Okay. Now I want to elaborate a little bit the capability of RNA laboratory in Lynas. So we have the capability of laboratory in Lynas from gram to kilogram scale before we are scaling to pilot and then for the industrialization. So of course we need to do RNI, research and innovation, in the small scale before we are scaling after the validation. So accelerating the market expansion, business growth. So this is very critical for the accelerating market. And then we want to strengthening the product testing and validation capabilities in this laboratory. And then demonstrating Lynas operational planning. Okay. And then achieving self-funded and self-sustained business. So as I say, we have a range of equipment in our laboratory for the testing of the materials, synthesis of the mixed oxide for fuel cell application, solid electrolyzer application, and then we have partnership with industries and external parties to validate the performance of the materials. So this is a kind of the how to establish the supply chain by validation of the materials before we upscaling in the industrial scale. And this is our central lab. So our RNA laboratory is supported by the central lab. Of course, central lab is support operation, daily operation in the Lynas operation. So we have some support here. As I showed, there are many processes. All this quality control is happening here in the central lab. And of course, the C lab has some analytical equipment to support our RNI operation, research and innovation, operation, investigation, and many more. And how the Lynas and Japan alliance. So this one I want to show how the alliance with the partners outside the China. As I showed before, the mining takes place in Australia, and then we bring the concentrate to the Malaysia for the separation. And then we have some metal industries, alloy industries, magnet industries, component and OEM. We will export all these raw materials to all these industries, including Japan, European countries, and the US partners, of course. So if you look here, all these materials is dominated by China, which is, I can say, the dominant by China is about 90% in this market. So Lynas is very critical in this area as a second source of materials for the solid oxide application and the rest of the materials, including magnet. Okay, so for EV car industries is very dependent on these rare earth materials. So it is very critical. The second operation, second source. We cannot too dependent on the first source. If we have any geopolitical issue, now we are facing that problem. So that's why Lynas want to extend the portfolio of the material production, not only produce the raw materials, cerium oxide, lanthanum oxide. We want to produce the materials for fuel cell application as well. Okay, we are not simply selling, so we want to extend our portfolio for the fuel cell materials. So we are not competitors for the fuel cell industry. We want to support the fuel cell industries in terms of supply chain. For the current program of Lynas in the solid oxides industries, If you see in the lab scale, producing kilogram scale batches of specific solid oxides, and then we need to necessarily step to be qualified as a potential supplier, and then we have to do some performance tests at the industrial partners location to validate our mixed oxide for the fuel cell application. Again, Lynas has the capability of producing scandia. So scandia is a gift from our thorium extraction. So this gift is huge amount. We have huge amount, and as it is good news for scandia stabilized zirconia based materials. The Lynas can be a supply chain of the scandia stabilized zirconia materials. Of course, the challenges is the zirconia based material. I'm not sure how the potential of zirconia in Indonesia. Probably you can share some information about the zirconia material capability. And then in RNI lab setup, we have set up RNI lab in Kuantan for the kilogram scale production and quick characterization capabilities, as I shown before, all the instrumentation in the laboratory before we send our sample for the validation to the customers. And then we also work closely with the universities and industrial partners for the range of solid oxide relevant to solid oxide electrolyzer or fuel cell operation, and then working on developing performance testing capability in-house and relying on the external resources, including leading universities. So ultimately, what I can say, Lynas is keen on collaborating, working with variety of industrial partners to develop next generation solid oxide for their specific needs to establish diverse and robust supply chain. So this is the ultimate goal of Lynas in these industries, including catalysts, okay, for the gasification. We also able to produce rare earth based catalysts for the ammonia cracking, for high temperature gasification. So all these are actually our interests in Lynas in the current geopolitical and current opportunities for the energy demand. Now, what is the synergism between the Lynas academy industries? I can summarize here. Lynas, we have formulation, we can do formulation, we can synthesis in program scale, we can do the process validation for the synthesis and characterization. So up to kilograms, the lab scale, this, and we know the know-how is Lynas capability to produce the oxides for the fuel cell application or catalyst or anything related to the gasification materials or catalysts we can do. So we have collaboration with industry. Once we are validated, so we can produce up to the hundreds of kilograms, and performance testing and industrialization with the industry partnership. We can do this. And then we also have some collaboration with industrial academia, local and outside external universities for some of the characterizations, fundamental characterization as what happening in the most of the local universities, which is very, very important for the industry partnership. Okay, so this is also one of the interests from the Lynas for the innovative formulation from the local synthesis and local characterization and performance testing. So this is how the synergism between the Lynas academia industries. So what I can say, the success for these industries, the supply chain of the materials is very, very, very critical, and we cannot very dependent of the single sole source, which is very, very a danger for the sustainability of this technology in the market. So this is my end of my slides. So thank you very much.
Thank you for the interesting presentation. So we will have some discussion. So there's someone who raised hand. So Mr. Ramakajo. So if you have question, I think Is it okay in bahasa? If the question is in
Baik.
bahasa. Okay. So,
Terima kasih
silakan,
Pak Moderator. Pak Mahendra bisa bahasa Indonesia ya?
Boleh faham sikit-sikit.
Boleh paham ya Pak?
Ya,
Pak,
boleh.
nomor satu, I should pass to you congratulations for Lynch rare earths activity in Southeast Asia.
Okay.
Selamat ya Pak, luar biasa, hebat sekali Bapak ini. Pertanyaan nomor satu Pak, Bapak refinery rare earth itu tanah jarang Pak, bahasa kita, tanah jarang. Bapak nomor satu ya di Southeast Asia ya, belum ada negara lain yang punya refinery yang seperti Bapak. Nomor dua Pak, Bapak dengan teman-teman itu yang bekerja di refinery Bapak itu semuanya orang dari teman-teman Bapak di Malaysia ya Pak, orang Malaysia ya. Luar biasa Pak. Selamat sekali lagi Pak. Nomor tiga Pak, resource Bapak itu dari Australia. Bahannya, the raw material come from Australia. Do you need some from us, from Indonesia? Kita juga punya Pak, rare earth Pak. Kalau Bapak mau, nanti saya kirim buat Bapak. Nomor tiga Pak, Bapak berdiri sejak tahun berapa Pak? When you start your company, it's long time ago or just a new established company. And berikutnya Pak, Bapak jual itu end produknya very sangat ini ya, sangat Bapak bicara sopan sekali ya. Bapak jual gram to kilogram bukan ton ya Pak. Luar biasa. Ya, sangat luar biasa Pak. Kalau kami ada minat untuk beli produk Bapak, saya bicara sama Pak Mahendra Rao atau sama siapa Pak? Itu saja Pak. Saya tidak bertanya detail-detail Pak, karena itu saya bukan ahlinya. Ahlinya itu Pak Rian itu. Terima kasih ya Pak Rao. Selamat buat Bapak.
Terima kasih Bapak. So saya komen sedikit. Boleh faham ya bahasa Malaysia?
Ya boleh bahasa Inggris Pak.
Okay, bisa. Okay. So yes, Lynas is the first refinery outside of the China. So established in Malaysia 2010 tak silap saya. Is established 2012 is full operation if I'm not mistaken. 2012 full operation, and the only separation company in the world outside China. So the only competitors. So we are actually, we can say about 10% of the world producer outside China. So Lynas, we are in that position. Lagi satu berkenaan dengan Bapak tadi di Malaysia. Yes, Lynas di Kuantan, Malaysia, almost 98 to 99% is Malaysian talents. So semuanya ialah orang Malaysia bekerja dan a few expats lah for the certain area. So 99% is Malaysians, 99%. Yang soalan seterusnya, yang rare earths daripada Indonesia, yes, Lynas happy to discuss sekiranya Indonesia wants to discuss regarding the availability of rare earths and processing at Lynas. Mungkin boleh email kepada saya more detail what kind of the collaboration that we can establish with Lynas in this processing, so I can have a good connection with the people from Lynas to discuss more detail on this interest from the Indonesia on this rare earths processing and then collaboration. Berkenaan dengan gram to kilogram, So I want to highlight this. Gram to kilogram here is we produce based on the demand from the customers in the industries. So customer will request based on our capability. So we need to validate ourselves. We need to fulfill all the requirements, all the impurities, all the specification. So we need to sell some samples to the industry. So the industry will choose if Lynas is capable of making that kind of materials to become a source of the second source of the materials supplier. Yes, we have a range of collaboration with the fuel cell industries to supply the gram to kilograms. So, but we are not producing fuel cell materials in the 100 kilograms up to tons. So this is under our next planning where we want to extend our portfolio. After we are in the we are also learning the curve of the demand, the market of the solid oxide in partnership with all these industries, because the capex is very high to establish this business in the Lynas. Fortunately, Lynas, we have know-how, and then we need to see how we can produce in the existing plant this solid oxide, mixed oxide materials. So this is the challenges that Lynas, but we know how to produce, how to make it, and how to fulfill the requirement from the industry. That's mean by grams to kilograms, what I mentioned. So saya rasa Bapak, saya sudah jawab soalan Bapak. Bapak daripada mana ya?
Pak, saya salah satu anggota di Indonesian Fuel Cell and Hydrogen Energy.
Oh, okay.
Ya, saya di situ. Terima kasih Pak Mahendra, luar biasa Bapak ini. Congratulations again for you.
Yeah, thank you very much.
Saya betul-betul sangat berbesar hati mendengar Bapak punya presentasi luar biasa. Pak, satu pertanyaan lagi Pak. Sedikit saja Pak, itu how many resource rare earth from Malaysia itself, including the Sabah and Sarawak, isn't it? Bapak jawab saya, ada berapa banyak Bapak punya rare earth di Semenanjung sama di Sarawak?
Okay, this is a good question. Yesterday I attended rare earth seminar in Putrajaya. So what the figure I found out from the government, so the calculated REE in Malaysia, the value is almost I think more than 800 billion ringgit. The value of the rare earths, more than that. I can say it could go up to 1 trillion ringgit Malaysia's, the value of the rare earths in Malaysia. So including all. So that's the figure I found out recently. Yes, we have a range of the discussion, even the local state governments with Lynas to establish this rare earths, like how the Indonesia is approaching Lynas currently to discuss on this possibility. Same thing is happening in Malaysia currently.
Pak Mahendra, terima kasih banyak Pak Hendra.
Terima kasih
once
Bapak.
Again, ya Bapak hebat.
Terima kasih.
Nah, Pak Rian, satu saya titip pesan Pak. BRIN, teman-teman BRIN, teman-teman IP, kita ada di mana? Itu saya jangan dijawab Pak. Kita ada di mana gitu. Saya prihatin Pak.
Terima kasih.
Ya jangan dijawab Pak. Saya prihatin Pak. Ini teman-teman supaya apa simpanlah mau kemana kita. Terima kasih Pak.
Terima kasih Pak. Thank you very much for the question. So we have a lot of questions to Dr. Mahendra. One question from Airlangga University. So I will just summarize his question. There are two questions here. First one, if the geopolitical tension disrupted, it will affect the rare earth export. So how resilient of Lynas' current strategy in ensuring the supply continuity for SOFC, SOEC manufacture? So that's the first question. The second question is that is there any roadmap developing recycled material to avoid future material breakouts? That's the second question. So please.
So the second question is recycling, you mean?
Yes, recycling.
Okay.
So roadmap for the recycling material.
So I answered the second question, the recycling. As I said, many of the fuel cell industries and electrolyzers, they're looking for these recycling technologies to sustain in this business, because you can separate all these scandia, all these expensive rare earths, especially zirconia, and to be close the cycle, rather than making the cell. We also need to know how to open the cell as well. Okay, so this is the roadmap is not very clear currently from the fuel cell industries, but Linus, we have the capability to test. If we get the samples from industries, we are able to do the testing of recycling of material. We have that capability. Of course, we have various discussions regarding this topic with a range of industry partners, how Linus can contribute in this area, recycling area. Yes, this is one of the interests from Linus as well, to support the fuel cell industries and electrolyzers. On the strategy of Linus, I think this is strategy of Linus in supplying the materials to fuel cell. Yes, that's why Linus is broadening the portfolio rather than just producing the oxide and selling the oxide to the various application for the catalytic converter, for LED TV, for the handphone, this, that, there, for magnet industry. So Linus want to produce the end product that is required by that industry. For example, fuel cell and electrolyzer, they need gadolinium doped ceria, for example. So we are not going to sell just gadolinium and ceria. So we will make the gadolinium doped ceria. It happened in Linus, and we will send the electrolyte, for example, to the required industries or required customer. So this is how Linus wants to be involved in the supply chain, because we have all the materials that required to make that happen. So this is the advantage of Linus outside of China. I think the Southeast region, including Malaysia and Indonesia, we need to take the advantage of this. How we can involve in this partnership with Linus to develop this rare earth processing, and then how we can work together on this. I think this is a interesting topic that we need to consider, because it is very lucky, very lucky, I could say, Linus in Malaysia, because without Linus, I think most of the industry will be suffering during today's geopolitical issue. Okay, and we have very good support from our partners from industries in Japan, especially for magnets, South Korea, US, and this. So that's why the alliance, if you see, Australia is not the sole dominant. So they are sharing the partnership with Malaysia, European countries, Japan, US. So if you see, the China is the dominant. We know China is the pioneer in this business in rare earth extraction, and so we need to take a piece of cake in this business to ensure this supply chain is sustainable in this current geopolitical scenario. Yeah.
Thank you for your detailed answer. So what I understand that so Linus can maintain the supply anytime, even with some geopolitical tension.
Yes. Seriously wants to involve in the supply chain for fuel cell electrolyzers, and also for magnet. Magnet is of course our established business. We are supplying the material. This is a new technology for gasification catalysts, fuel cell materials. So we are able to do that. We have the know-how know-how industrial to produce this. Yeah.
So, would you mind to move to another question? So this question is a bit technical. So I think I hope you don't mind if this technical question appears. So this from Jaran University. So the metal exhaust perovskite are viewed as the promising solution for carbon and sulfur tolerance. What are the main durability challenges during this long-term operation? And what approach are being developed to keep this nanoparticle stable and active over time?
Okay, I think it is exhaust nanoparticles, I think. Yeah, in the current solution for the fuel electrodes of current scenario. So what the many researchers is doing is they use the exhaustion of the metal. So the nanoparticle will be absorbed under the hydrogen environment. So that catalyst will improve the oxidation of fuel and reduce the carbon deposition. So this is something like you produce the perovskite based material, and then you reduce it under the hydrogen environment. And then, for example, the nickel will be absorbed from the perovskite structure. From the B side, we have A side and B side. From the B side, it will absorb, and it will form a catalyst on the layer. It is something like the modifying the surface of the electrode with absorbed nanoparticles to improve the overall performance of the electrode under the hydrocarbon fuel situation, which can reduce the carbon deposition, sulfur poisoning. Meaning this is a new one of the ways to mitigate the nickel coarsening and nickel degradation issue in the conventional electrodes. So this is the one of the issue that with these materials is we need to consider about the overall conductivity. We need to consider under that condition. So the key reason for the exhaustions is to mitigate some of the chemical issues, the sulfur poisoning, carbon deposition, this for long-term stability. Yeah, I hope I answers these questions.
Thank you for the thorough answer. So this is new, how to say, new road to mitigate that kind of the poisoning. So by kind of nickel exhaustion is quite interesting route for to tackle this poisoning. So there's another question again. So SOFC now is toward lower operating temperature. So what kind of strategies that most effective to keep high oxygen ion conductivity and good efficiency when we use electrolyte beside zirconium? For example, if we use ceria-based electrolyte.
If I understand this question, this one is how to keep the conductivity.
Yes. Okay. To keep high ion conductivity.
This is very common. Even Kawada already explained in detail. The selection of materials actually according to the operating conditions, temperature. If you use YZ material, the conventional, the traditional zirconia-based material, you have to operate at temperature more than 800 for efficient hopping mechanism. We call hopping mechanism, the oxygen ion traveling from the cathode to anode of solid oxide fuel cell. So the hopping mechanism will be more efficient at high temperature for zirconia-based material. For CGO, the hopping mechanism is efficient at the temperature lower than 600. If you go more than 600, there will be some issues of the what we call electronic conduction issue, and there are many issues. So the selection of material, if I say between a range of material, of course, a zirconia-based material is the best, cheap, and very, very stable material compared to ceria-based material. So that is why people use zirconia-based material. Until now, this material is still a demanding material for the fuel cell and electrolyzer industries for solid oxide. So we have two ways. Either you change the material to reduce the operating temperature, or you control the manufacturing process. For example, you use the very thin layer of the electrolyte to compensate the polarization resistance in the electrolyte. Okay, because when you reduce the temperature, the oxygen ion needs a longer path to travel in the thick electrolyte. If you reduce the thickness of electrolyte, so the distance is shorter, so you can compensate some of the losses. Okay, so this is how the trade-off between the operation temperature and cell fabrication. So this is how the fuel cell industries actually is doing the business, whether they are going electrolyte supported, electrode supported, is based on the material selection and then the operation conditions.
Yeah. So what I understand that if we use ceria-based electrolyte, so we have to consider that the ceria is kind of mixed conductor, so it's not ion conductor. So in the electrolyte case, we need only to transfer the ion conductor, but in the GDC case, CGO case, so it's not ion conductor only, but also electronic can conduct in this. So that's
not like that. All the electrolyte must be ionic conductor.
Yes, must ionic conductor. So yes, that's
the conduction mechanism when you change the temperature for CGO. If you go beyond 60, there's some issue. And then the oxygen partial pressure also can change the conduction behavior from the ionic to electronic. So this is the things that instability of CGO at higher temperature. It must be operated at lower temperature. Yeah. So Linus is capable of doing all these mixed oxides. Actually.
Thank you. So this is another question. So I think the same question about recycling of the SOFC and SOFC component. So how the industry integrating large-scale recycling into the commercialization roadmap to mitigate the supply risk? That's the question.
I think this answer I already give previously. Same question.
Yes, I agree.
I think the same answer. What I say, currently there is no clear recycling industry for fuel cell sectors currently, but I would say, based on my discussion with many industries wants this technology, recycling, and Linus willing to step in this technology, recycling, because we know how to produce the oxide. So how the root, everything, we know how to separate all these materials from the solid phase. This is also solid phase, but very stable. The thing is, zirconia is very, very stable. So very, very tough to separate. So that is what challenges for zirconia based material. So yeah, Linus actually very interested in this technology, and we are also in discussion with a few industries how to materialize this recycling cycle in the solid oxide fuel cell industries.
Yeah, thank you. So actually, it's complete the answer. The previous question also asking about the recycling, and also just also another question about recycling. So we have one last question. Is it okay for you?
Yeah, okay, no problem.
So if I can summarize, so in terms of SOFC efficiency, since SOFC working at high temperature 600 to 1000 degrees C, what proportion of the produced energy is typically used to maintain the cell operating temperature? So that's the first question. So second one is, which component primarily requires such high temperature? The electrode or the electrolyte? I think it's supposed to be both. Okay, so first question. So how we can maintain the cell operating temperature during the operation?
I think maintaining the cell operating temperature. I think this is This is what we call combined heat and power integration in the plant. So this is how the industries, that's why the solid oxide is very useful for the industries, as it generates a lot of heat. So the heat can be just can be integrated for other processes, or we just use as a heat in the buildings, for example, or we can use the heat for other steam generation, for the steam generation, gas plant or power plant, we can use that. So I think this has been shown by Prof. Kawada in detail. How to maintain the temperature? Yeah, I think the integration of the system is very important for me. Okay.
So, I think it's not a difficult question. So, which component primarily requires such high temperature?
All the components you need to fabricate, you need to sinter at high temperature. In all the components, I would say need more than 1000 for current condition to fabricate all the components for the solid oxide cell. Electrolyte is slightly higher temperature you need, can go up to 1400 or 500 to make it dense, because the electrolyte must be dense enough without any holes or pinholes. But the electrodes, you know, it should be porous structure, and the temperature, we are not going very high temperature as well. If you go very high temperature, perhaps we will lose some of the porosity in the structure. So
yes. Would you mind if I have one question for you?
Yes.
So in Lynas, do you also produce proton conductors such as barium cerate or barium zirconate?
Yes, we can produce. We can produce PE proton expansion, but currently in the current fuel cell industries, most of the demand is the traditional material. So proton conducting is the next generation material for the fuel cell. Yeah. So we are working based on the customer demands on this kind of the materials. So most of industries actually, they are looking at the traditional zirconia based material, and the demand for scandia is very high current. And then for the perovskite based material for the electrodes, okay, this is a kind of the materials which is well known for the in the industry. The fuel cell industry people, they know what the materials they prefer for the manufacturing of the cells. Yeah. So yeah, proton conductor. Yes, I have done a lot of work on proton conductors. So, but in terms of the industries, they haven't used that kind of materials yet for the real operation in the industry. From the best of my knowledge, no such a big stack that has been built and demonstrated currently in the industries. Maybe it is there, but maybe I don't know. So let's see if there is anywhere there's good news for Lynas as well. Why not?
Yeah. Thank you. Mr. Makajo, I think still has question for you.
Pak Moderator, tolong tanyakan Pak, untuk refinery mereka ini, untuk refine itu semua, energinya dari mana Pak, sumber energinya? Itu aja Pak.
Yeah, we have our, because this is high temperature of calcination we need in our plant, and we have extraction, liquid solid extraction, and then we also need some steam in the industry, the steam requirement. So that is more on the upstream works. In Lynas, yeah, we call downstream, but not very downstream. So we assume the very downstream is the production of materials for solid oxide application. Okay, so yep, the industry we currently use from the energy from the grid line from the TNB from Malaysia. Yeah, currently. Yeah.
Thank you Pak. Yeah. Pak Mahendra, terima kasih Pak.
Terima kasih Bapak.
Terima kasih Pak. We don't have any more question. We will close the discussion for the second presenter. And before we close this session. So I would like to give you the certificate of appreciation. So would you mind to take picture? So please wait.
Yes.
Thank you very much. For your interesting talk and also answering the discussion and many questions from the audience. So the talk session is over. So I will return it to the Miss Danisi. Please continue. Thank you very much for the presenter today. Thank you.
Thank you. Thank you.
Baik, demikian tadi telah kita simak bersama sesi utama pada webinar kali ini, yaitu sesi presentasi dan diskusi atau tanya jawab. Terima kasih Dr. Yan. Kita juga ada sertifikat untuk moderator sebagai tanda terima kasih telah memandu acara webinar pada hari ini. Boleh dibantu untuk panitia untuk menampilkan sertifikat untuk moderator kita. Baik, sekali lagi kami ucapkan terima kasih untuk Dr. Yan yang telah berkenan memandu acara pada hari ini. Kita berikan tepuk tangan. Baik, sekali lagi terima kasih kami sampaikan kepada Dr. Yan selaku moderator serta para narasumber, Profesor Tatsuya Kawada dan Dr. Mahendra Rao Somalu atas materi dan diskusi yang sangat bermanfaat pada hari ini. Thank you very much to Professor Tatsuya Kawada and Dr. Mahendra Rao for sharing valuable knowledge with us today. Dan terima kasih juga kepada seluruh peserta yang telah berpartisipasi aktif dalam acara ini. Sekali lagi kita berikan tepuk tangan virtual untuk para pembicara dan juga moderator kita. Baik, oke, terima kasih. Jika masih ada pertanyaan, mungkin nanti bisa diajukan lewat email begitu ya. Dan untuk materi webinar, kami sampaikan dapat Bapak Ibu simak kembali rekamannya di kanal YouTube IFHE Official. Sekali lagi kami ucapkan terima kasih atas antusias dari Bapak Ibu semua. Dan kami ingatkan kembali bagi Bapak Ibu dan peserta webinar yang belum mengisi daftar hadir, agar dapat mengisi daftar hadir yang telah kami share di kolom chat. Dan mohon dipastikan data yang diisikan telah sesuai karena akan digunakan sebagai data pada sertifikat peserta. Terima kasih. Baik Bapak Ibu dan hadirin yang kami hormati, tibalah kita di sesi pengumuman pemenang door prize. Sebagai bentuk apresiasi kepada para peserta yang telah aktif berpartisipasi dalam webinar hari ini, panitia telah menyediakan door prize untuk 3 orang penanya dengan pertanyaan terbaik. Untuk itu, dengan bangga kami umumkan pemenang door prize pada hari ini. Pemenang yang pertama, Bapak Wildan Baina El Islamik dari PT PLN. Pemenang kedua, Ibu Eka Galuh Puspita dari Pajajaran University. Dan pemenang ketiga, Bapak Utama Kayo dari HIMN Indonesia. Selamat kami ucapkan kepada seluruh pemenang. Terima kasih atas kontribusinya dalam diskusi yang sangat inspiratif dan memperkaya sesi diskusi kita pada hari ini. Sekali lagi kita berikan tepuk tangan yang meriah untuk para pemenang. Dan untuk konfirmasi pengiriman hadiah, kami mohon kepada para pemenang door prize agar dapat menghubungi panitia via WhatsApp, DM Instagram, maupun email pada kontak yang telah kami cantumkan pada flyer webinar. Atau bisa juga telah mengisi daftar hadir dengan data yang lengkap agar dapat dihubungi oleh panitia. Baik Bapak Ibu, kembali lagi kami ingatkan bagi Bapak Ibu yang belum mengisi daftar hadir agar dapat mengisi daftar hadir yang telah kami share di kolom chat. Baik Bapak Ibu dan hadirin sekalian, demikianlah tadi seluruh rangkaian acara e-Talks ke-16, webinar series on clean energy and advanced materials telah kita lalui sampailah kita di penghujung acara yaitu penutup. Atas nama panitia, kami mengucapkan terima kasih kepada seluruh narasumber, moderator, dan seluruh peserta yang telah hadir dan berpartisipasi aktif. Kami ucapkan terima kasih juga kepada para sponsor, PT Hyoki Electric Instrument, PT ITS Science Indonesia, dan PT PLN Nusadaya atas dukungannya. Webinar ini juga disiarkan secara langsung melalui kanal YouTube FAI Official dan dapat Bapak Ibu simak kembali. Semoga kegiatan pada hari ini dapat bermanfaat bagi kita semua. Sekali lagi kami mohon maaf jika ada kekurangan dalam penyelenggaraan acara ini. Sampai jumpa pada acara webinar series on clean energy and advanced materials berikutnya yang ke-17, yaitu pada tanggal 3 Desember mendatang, dengan pembicara dari PT PLN dan juga Tokyo University. Kami informasikan IFAI akan mengadakan event Global Hydrogen Ecosystem Summit atau GHS di bulan Juli tahun 2026 mendatang. Adapun acara webinar hari ini merupakan bagian dari Road to Global Hydrogen Ecosystem Summit. Kami nantikan partisipasi Bapak Ibu di acara GHS nanti di bulan Juli 2026. Baik Bapak Ibu, kita tutup acara ini. Sedikit pantun penutup. Solid oxide cell kian berkembang. Logam tanah jarang jadi andalan. Terima kasih Bapak Ibu yang telah datang. Sampai jumpa di webinar ke depan.
Cakep.
Oke. Satu lagi. Solid oxide cell wujud nyata dengan logam tanah jarang di dalamnya. Energi bersih bukan sekedar wacana. Mari kita jaga bumi bersama-sama.
Cakep.
Baik, mari kita tutup acara ini dengan hamdalah, syukur alhamdulillah, Hirobil alamin, dan tepuk tangan virtual untuk kita semua. Selamat siang, wassalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua.